Okay, so in this video I'm going to do another example of finding the Laurent series. Um, and this time I'm going to show you how you can find the Laurent series in multiple regions sort of at the same time. Because often you get a question like this, like the question I've written down here. They give you a Laurent series and they give you a function, sorry, and they ask you to find the Laurent series in a few different regions. And I just want to show you how you would efficiently set out your working. So here, my function, it has singularities, so it's not defined at 5 and 12. So, and because you need your function to be analytic in the region where you find the Laurent series, we can find the Laurent series when modulus of z is between 5 or 12 or outside 5 or 12. And that's what parts A, B, and C are saying. So how do we do this? Well, first thing I do, I have to decompose f into partial fractions. So I'm going to write f of z equals a on z minus 5 plus b on z minus 12. And of course, for this to work, I'm going to need 5z minus 39 to equal a on z minus 12 plus b on z minus 5. So if I sub in z equals 12 into this equation, on the left I get 21. On the right I'm just going to get 7b. So therefore b is equal to 3. If I sub in z equals 5, on the left I get negative 14. On the right I'm going to get negative 7a. So therefore a is equal to 2. So therefore f of z is going to equal 2 on z minus 5 plus 3 on z minus 12. Now, remember, I know how to find the Laurent series for 1 over 1 minus z, that geometric series. I can do that when the modulus of z is greater than 1 or less than 1. And if you remember from the previous examples, really all we did was we replaced z with something else to get the Laurent series we want. Here, because I have z minus 5 and z minus 12 on the denominator, I can already see that I'm going to be taking that result from before, and I'm going to be replacing z with z on 5, or replacing z with z on 12. So I may as well just go ahead now and rewrite f in terms of those two. So what I mean is, I can write this as minus 2 on 5 minus z, minus 3 on 12 minus z, and then going even further, I can write this as minus 2 on 5 times 1 over 1 minus z on 5 minus 3 on 12 over 1 minus 1 minus z on 12, right? And then what I do, I write that important result from before. So this one, as you can see, it's extremely important because you use it over and over. So I'll write it as, recall, if you have 1 over 1 minus z, you can write this as sum from infinity, from n equals 0 to infinity of z to the power of n, if modulus of z is less than 1. Or you can write it as minus sum from n equals 1 to infinity of 1 over z to the power of n. And remember, that's if modulus of z is greater than 1. Okay, so what I'm going to do is now I'm going to replace z with z on 5. Okay, see what I get. If I replace z with z on 5, then this guy becomes 1 on 1 minus z on 5 is equal to sum from infinity n equals 0, 1 on z to the z on 5 to the power of n, if z on 5 is less than 1, or in other words, modulus of z is less than 5, and the bottom half will become infinity sum from n equals 1 to infinity negative 1 on z on 5 to the power of n if modulus of z on 5 is greater than 1, or in other words, modulus of z is greater than 5. Okay, now if I take that same result and I replace z with z on 12, what do I get? I get 1 on 1 minus z on 12 equals sum from n equals 0 to infinity of z on 12 to the power of n. Again, that's if z on 12 is less than 1, or in other words, modulus of z is less than 12. Or the bottom half, I get this. Right? And this is when modulus of z on 12 is greater than 1, or equivalently, modulus of z is greater than 12. So I have these 4 different series expansions. And what I'm going to do, I think the best approach to set out your work is to label these ones. So I'm going to call this 1, 2, 3, and 4. Okay? Now let's have a look. If you have a look at part A in red, we want a series for f that converges when the modulus of z is between, well, it's less than 5, put it that way. Right? Now, for the modulus of z to be less than 5, I can just combine series 1 and 3. Because 1 holds when the modulus of z is less than 5, 3 holds when the modulus of z is less than 12. So when I add them, they are both still going to converge when modulus of z is less than 5. And that's going to be the answer for part A. So you can write it like this. For part A, you can combine 1 and 3. So what do you get? You get f of z is equal to, so it's going to be negative 2/5 times the series from 1. So remember, just recall, this is what f is given by, right? So it's going to be negative 2/5 times the series in 1, which is the sum from infinity, from n equals 0 to infinity of z on 5 to the n minus 3 on 12 times the series in 3. Yes? So what I'm going to get is I'm going to get the following. This is going to be sum from infinity n equals 0, negative 2 on 5 to the n plus 1 times z to the power of n minus sum from n equals 0 to infinity 3 on 12 to the n plus 1 z to the power of n. And I guess you could combine those two. It's pretty easy to do it in this case. So you can write it as sum from n equals 0 to infinity of negative 2 on 5 to the n plus 1 minus 3 on 12 to the n plus 1 z to the power of n. Yep, simple as that. So that would be the power series for part A. Now for part B, let's have a look. For part B, I want the modulus of z to be between 5 and 12. So I want the modulus of z to be greater than 5, and I want the modulus of z to be less than 12. So I can just combine series 2 and 3, right? So for B, we're just going to combine, oops, sorry about that. We're just going to combine 2 and 3. So what do we get? We get f of z again, it's going to be minus 2/5 times the series in 2. So the series in 2, you can write that as, I guess the series in 2, you can write that as negative 5 to the power of n on z to the power of n. Yeah. Then I'm going to do minus 3 on 12 times the series in 3. So I'm going to write it like this. So now this series on the left can be written as 2 times 5 to the n minus 1 on z to the n minus infinity n equals 0, 3 on 12 to the n minus 1 on, actually it should be 12 to the n plus 1, sorry, z to the power of n. And that will be the answer to part B. So this will converge when the modulus of z is between 5 and 12. Now have a look at part C. Now we want the modulus of z to just be greater than 12. Okay, so if we want the modulus of z to be greater than 12, I can just combine series 2 and 4, can't I? Because series 2 converges when modulus of z is greater than 5. Series 4 converges when modulus of z is greater than 12. So when you add them, both of them are still going to converge when modulus of z is greater than 12. So for part C, I'm going to combine 2 and 4. So f of z is going to be minus 2/5 multiplied by the series given in 2, which I can write as minus 5 to the power of n on z to the power of n. Then I have to do minus 3 on 12 times the series given in 4, which I can write as minus 12 to the n on z to the n. Okay, so let's tidy this up a little. So this is going to become positive 2 times 5 to the n minus 1 on z to the n. This one is going to become positive as well. It's going to be 3 times 12 to the n minus 1 on z to the n. And I can add these guys, I guess. So this will be sum from n equals 1 to infinity 2 times 5 to the n minus 1 plus 3 times 12 to the n minus 1 all over z to the n. So this one only includes negative powers. So that's an efficient way of answering this sort of a question. Write out your 4 possible series expansion before you sort of get into the question itself. Then for each part, see which series you need, and then just add them as appropriate.